So if we look at how these subatomic particles make up the atom, we can say that in the nucleus, or in the center of the atom, the protons and the neutrons are contained. Okay? We have positively charged particles and neutral particles. So here is our nucleus. It's going to be positively charged. And since it has the protons and neutrons, the mass containing subatomic particles, it's going to be very, very dense. The electrons are going to orbit the nucleus. So here we have our electrons out here orbiting the nucleus. These are going to be negatively charged. And they are in constant motion. So this is our relative generic structure of the atom. We'll get into this later in Chapter 8 and Chapter 9 and discuss all of these subatomic particles, how they're going to interact, how they're going to bond with each other, and everything like that. But before we get there, again, let's keep laying the foundation here and talk about how each of these subatomic particles come together to make up or to describe what an element is. So an element is characterized by the number of protons it contains. We have a term for this. The number of protons is going to be equal to the atomic number. And the atomic number is typically abbreviated with a capital Z. If we vary the number of protons, we are going to change the identity of one element to another element. So with each element, they are defined by the number of protons that are going to be present. We can now put together symbols for these particular elements, and they take on the following generic form. If we have an element symbol X, we need to now describe how many protons and neutrons there are in this particular element. So typically, we have a notation where we have the element X, then we have a subscript over here on the left, or a superscript on the left and a subscript on the left that we refer to as A and Z. A is going to equal the atomic mass. And remember, the atomic mass is going to be the sum of the protons plus the neutrons. Z is our atomic number. The atomic number is simply the number of protons. So if we look at how we define each of these elements, we can look at oxygen. Oxygen, if you look on the periodic table, has an atomic number of 8. So Z is going to be 8, so we're going to put that down here in the lower left-hand corner. We can now look at each of these oxygens and figure out how many protons and neutrons they have, and this can potentially vary. So this is why we come up with this symbol notation. If I have a 17 as the mass number, we can directly look at this symbol and indicate how many protons there are on this atom. The number of protons we have are 8, because that is going to be the atomic number that's listed down here. The mass number is going to be 17, so the protons plus the number of neutrons has to equal 17. If we have 8 protons, That means we have 9 neutrons. The number of electrons is going to be indicated by the charge. Typically, we will put the charge right around this spot right here in our symbol. If it's not a charged particle, if it's neutral, it's going to be blank, right? We don't write the 0 up there. So that means that the number of protons and the number of electrons has to be equal. So if we have 8 protons and we have a neutral particle, that means we have 8 electrons. If we do one more example and we look at californium, which is abbreviated CF, and if it has a mass number of 251 and an atomic number of 98, we can indicate how many protons, neutrons, and electrons we have. The number of protons is the easiest. That's going to be the atomic number. We have 98 protons here. The number of neutrons is going to equal 251 minus 98, which would be 153. And the number of electrons is going to be equal to the number of protons in this case, because we have a neutral species here. So we're going to have 98 electrons as well. What we're going to look at next is what happens when we have an uneven number of protons and electrons in a particular atom or element.